Welcome to Topology Lesson 11. This is about metric spaces and the particular topic of compactness. Compactness is sort of a generalization of closed and bounded, and we'll do some definitions in this lecture, a few examples, and a few theorems. As I mentioned on the previous slide, compactness is a property that generalizes the notions of closed and bounded sets from Euclidean space. We have a definition here from Wikipedia, or at least sort of an overview statement. So let's look at that. In general topology, compactness is a property that seeks to generalize the notion of closed and bounded subsets of Euclidean space. The idea is that a compact space has no punctures or missing points, i.e. it includes all limiting values of points. For example, the open interval 0, 1 would not be compact because it excludes the limiting values 0 and 1, whereas the closed interval would be compact from 0 to 1. Similarly, the space of rational numbers Q is not compact because it has infinitely many punctures corresponding to the irrational numbers. So the rational and irrational numbers are very much intertwined, and you can't put an open ball, for example, around any rational number without including irrational numbers, and vice versa. Excuse me. The space of real numbers is not compact, and that's because of the bounded condition here. But if you take the extended real number line, where you include the plus or minus infinity, then it would be compact in that case. The term punctures in the description from the previous slide is a bit misleading, and we'll see an example of that in the next slide. This slide actually has sort of a valid puncture in it. Let me just explain the figure first here on the left. So we have a closed disk, including its boundary. We have the point 1/2, 1/2 missing. So this little white thing here is removed. And the idea is to avoid subsets of a metric space that have sequences that converge but not within the set. So I've just defined this sequence here, 1/2 minus 1 over 2 to the n, 1/2 minus 1 over 2 to the n, which starts at 0 and then moves along, getting closer and closer and closer to the missing point, the puncture, so to speak. And so it does converge, but it converges to something not in our set as we've defined it. So this set here is not compact. Now on this slide we have an example of where we do have a puncture. The thing on the left, the set on the left has two punctures in it, but in fact it is compact. It contains all its limit points, and of course you can see it's bounded. So the boundary of A and B are included, and so there's no point in the gray set, including the two boundaries, that is a limit point but not included in the set. So this is fine, this is compact. But on the right we do have a problem. You notice we've excluded the boundary of B. We removed A and B, disk A and B, but we've kept the boundary here and we've removed it here. So again, any point along this boundary is a limit point to sets, many different sequences in the gray area here, but it's not included in the set. So this is not compact. Set on the right is not compact. So let's look at the formal definition of compactness. You may also want to have a look at this YouTube video that someone else put together. I think it's very good. It rationalizes why compactness is defined as it is. And I'll put the link in the description to this video. But let's look at the definition. So a metric space X is compact if every open cover, in other words, a collection of open sets such that X is, every element of X is in this union, has a finite subcover. So for every cover of open sets, of which X is a subset of the union. You should be able to pick a finite number of these such that X is still a subset of the union of the finite collection. What it's not saying is that X is compact if it has a finite cover, I should say, finite cover. That's always true. You can always just take X, and X would be a subset of itself, and that's doesn't mean it's compact. What compact means if you take any possible cover, then you can pick a finite number of these and get and still cover X. That's what it means. We'll see some examples that maybe will help clarify this a little bit. Yeah, and just maybe one other point here. So the definition can be, this can be rather hard to apply, but we have some equivalent definitions or equivalent conditions for compactness, which I'll state. Some of them are in general, and then at the very end of the presentation, there's another set of conditions that apply just to n-dimensional Euclidean space, where it's rather easier to determine if something is compact. We have three conditions that all imply compact. The first one is the definition itself. In every open cover of metric space, X has a finite subcover. That's equivalent to every sequence in X having a convergent subsequence, and that's equivalent to the metric space being totally bounded and complete. If you recall, complete means every Cauchy sequence converges to a point in the metric space, and totally bounded is defined right here. A metric space is totally bounded if for every epsilon greater than 0 there exists a finite number of open balls of radius epsilon that cover X. I have a proof, or at least I point to a proof in the book by Gamelin, Introduction to Topology. And I have the detailed reference to that book in my book, reference 71, which you can download. Mentioned that several times. The book is Mathematical Vignettes, Volume 3. Let's give a definition of bounded. I think it's kind of intuitively clear, but this is a more precise definition. So a metric space is bounded if there exists m greater than 0, such that the distance between any 2 points in our metric space is less than m. Totally bounded is a more stringent condition than bounded, and in fact that's the case, and we'll see that in the theorem in the next slide. A totally bounded metric space is also bounded. We'll see on the next slide that bounded doesn't imply totally bounded, so the converse is not true. We can prove this. Since X is totally bounded, then we can pick any epsilon. We'll pick epsilon equal 1 such that there's a finite number of open balls of radius 1 where the set X is a subset of the union of these open balls. Let m equal 2 plus the maximum distance between any two open balls in our set here of open balls. And we're going to show that any 2 points in X are at a distance less than m. If X and Y are in X, then we have two cases. X and Y are in the same open ball, in which case since the open balls in this example have radius 1, but diameter 2, then the distance between X and Y is 2 at most. And if X and Y are in different open balls, let's say this one here and this one here, then we can apply the triangle inequality twice. First, based on xi, and we get the distance between x and y is less than this. Then we apply a second time the triangle inequality on this term here, We get this. And then since x is in this open ball, this distance is less than 1. And since y is in this open ball, this distance is less than 1. And then this distance between the two centers is of course less than the maximum distance between any two centers. So we get 1 plus this max plus 1 again. We get 2 plus the maximum distance between the centers of any two open balls, and that's what we called M. And so either way, the distance between x and y is less than M, and so our set is bounded. Converse of the previous theorem is not true, and we have a counterexample to this. Let's take the set of natural numbers 1, 2, 3 up out to infinity with the discrete metrics. Remember, we defined that very early in our lesson on metric spaces. It's the distance between any two distinct points is 1. So if x and y don't equal each other, we get the distance being 1. And if, well, by the definition of metric, if it's the same, the distance between a point and itself is 0. That's required for a metric space. So the set n is bounded because for any two elements in the set, the distance is always 1. So we know the maximum distance is 1. So that gives us a fairly simple proof that it's bounded. But it turns out n is not totally bounded. And we can show that. We can pick any e. Recall for the definition of totally bounded, we can find a finite number of balls, open balls, that cover each point in our set, that include each point in our set. So if we take epsilon less than 1, then we would need an open ball to cover 1, and that would not be able to reach 2, so we need another open ball for that, and another open ball for 3, and we would have no way of covering the natural numbers with open balls whose radius is less than 1. So that means it violates the definition of totally bounded. We have another example here of a set that's bounded but not totally bounded. Let's look at the subset of points in an infinite dimensional Euclidean space, such that there's a 1 in just one position and a 0 everywhere else. I've shown the first few elements here. You have a 1 in the first position and all zeros, 1 in the second position, 0 everywhere else, 0 in the third position, 1 in the third position and a 0 everywhere else, and so on. So we have an infinite number of these. Then we'll define the metric between the distance, in other words, between 2 points, is just the maximum of the distance on a pairwise basis. So if you took these two here, the first distance, this one here, would be 1. This would be distance 1, and then 0, 0, 0 everywhere. So the max would be 1, and no matter what two you pick, you're going to get 2 of these being 1 and the rest being 0. So the max would be 1. Yeah, and the distance d sub 1 is just the one-dimensional Euclidean space distance, the distance between two numbers. So the set y is bounded because the distance between any 2 points is 1. We can just take m as our bound, and then everything is less than m. However, if we choose a radius epsilon less than 1, then it takes an infinite number of open balls to cover all the points in y, and thus y is not bounded. So keep in mind, if you have a radius less than 1, then you're only going to include, if you take this point and an open ball radius less than 1, it only is going to include this point. The same thing here and here. So again, we have an infinite cover of the set, but there's no finite subcover. So this is not bounded, and it's not totally bound, excuse me, and it's by implication, it's not compact. And we'll see in the next slide that we have a weaker condition for compactness in n-dimensional Euclidean space. We don't need total boundedness, we just need boundedness. A subset Y of a metric space X is said to be a compact subset of X if every open cover of Y in X has a finite subcover. We have a theorem related to compact subsets. For a subset E of n-dimensional Euclidean space, we have the following equivalent conditions. This is a definition here, which we just stated. That's equivalent to every sequence in E having a convergent subsequence. And then that's equivalent to E being closed and bounded, which is useful here. So we don't need totally bounded in this case. Here we have an easier way of determining compactness for a subset of n-dimensional Euclidean space. Here we just need to know the subset is closed and bounded. So closed, and it contains all its adherent points, and bounded is, as we described before, the maximum distance between any 2 points is less than some particular number. And that proof can be found if you're interested in the Wikipedia article entitled Heine-Borel theorem. Okay, so that's the last slide in this particular lesson. We have one more lesson on metric spaces, which is lesson 12.